Hello everyone, welcome back to Nated Engineering. Today we are doing velocity diagram, power machines and 6. We already know what a velocity diagram is and what is it that is being represented by a velocity diagram from power machines and 5. A quick recap from what we did on power machines and 5. We know that the velocity diagram is a diagram that we draw to represent in terms of velocity and angles what is happening with the steam as it is entering the steam turbine, which we are using to generate electricity. So now we know that there are types of velocity diagrams. We have types. We have an impulse turbine, where they will tell you to draw a velocity diagram with axial thrust. So whether they tell you about an impulse turbine, this will be an impulse turbine, or they tell you about a velocity diagram with axial thrust, you must know that they are referring to the same thing. And the velocity diagram of an axial thrust or the velocity diagram of an impulse turbine or the velocity diagram with axial thrust, this is the type of a velocity diagram with an axial thrust. And then we go to the next one, which is a reaction. And they will tell you that it's a velocity diagram without axial thrust. So whether they tell you about a reaction turbine or they tell you about the velocity diagram without axial thrust, you must know that they are referring to the same thing. So what is meant by this is that here you are going to have two identical triangles. So if you are drawing the velocity diagram of a reaction turbine or the velocity diagram without axial thrust, we are going to have two identical triangles, something like this, where this will be equals to this will be equals to this, and these triangles will be the same. Also, these triangles will be the same. So basically what you are going to have is two identical triangles when you are told about the reaction turbine or a velocity diagram without axial thrust. And then we have the last one, which is the one that discharge axially. A velocity diagram that discharge axially. Whenever you are told about a velocity diagram that discharge axially, we are going to have something like this. Before you read anything, you must know that this angle will always be 90 degrees, which is the outlet angle of the steam. And then you can get from the information the other things that they are telling you about. But this is the first step that you must consider when you are told about a velocity diagram that discharge axially. So we come back to the diagram. We know we are having the nozzle, in this case, being placed in this position. So as the steam is leaving the nozzle into the blade, it will be leaving the nozzle at a certain angle, which is the nozzle angle, or you can call it the inlet angle of the steam, which is this one. As it is leaving the nozzle, it will be leaving the nozzle at a particular angle and entering the blade at velocity number 1. That is the speed of the steam as it is leaving the nozzle. And then it will leave, after gliding through the blade, it will leave the blade at velocity beta. And then this u will be the velocity of the blade as it is moving to that direction. And then these two will be the relative velocities. This will be the relative velocity between the inlet angle and the blade, and this will be the relative velocity between the blade and the outlet angle. From this point to this point, or we can say from this leg to that leg, we are going to have VWT, and then this component and that component, this will be the velocity of flow number, say velocity of flow number 1, and this will be the velocity of flow number 2. So these two angles, this is the inlet angle of the blade, and this is the outlet angle of the blade. The steam will be entering the blade at a particular angle, yes, but the blade itself has its own angle, which is represented by this one. And then at the outlet also, the blade has its own angle, which will be represented by this theta. So this will be theta, and this will be the phi, and then this will be the alpha, and then the angle at which the steam will leave the blade, that will be what we call our beta. So this is what we know from power machines N5. So even now, nothing is changing. We are just advancing from what we know. So this is what we have now. Now, instead of dealing with one blade, we will be dealing with two blades, giving us a two-stage velocity diagram. So what we want now is, we want the steam to glide through this blade and then to glide also through this blade. What we need to introduce is what we call a fixed blade. This one is fixed. Meaning it is not moving. So what is going to happen is the steam will glide through this blade, and then this blade, it's used to redirect the direction of the steam so that it is able to enter even the second stage. This will be the first, and this will be the second stage. So this is a fixed blade. The steam will glide through the first moving blade, and then it will be redirected by the fixed blade to enter the second moving blade, or the second stage. So as a result, we are going to have two diagrams, each diagram for each blade. The large diagram is the diagram for what is taking place on the first stage, and the second diagram is the diagram for representing what is taking place at or in the second stage. So what is going to happen is, our nozzle is here. The steam will enter at velocity. Now we are going to change the values since we are having two diagrams. We have to make things simple. I am going to call this V initial, and then I'm going to say, we will say this is the nozzle. The steam is entering the first stage at velocity V. It's V initial, or the inlet velocity. It's entering. This is the angle of the nozzle, and then it will glide through, and then it will leave the blade at velocity E, which we are going to say it's the exit velocity. So now, since this is the first stage and this is the second stage, you have to represent that by saying this is number 1, and also this is number 1. This we know it's the inlet velocity of the, it's the inlet angle of the blade, and this is the outlet angle of the blade. This is the outlet angle of the steam. So I'm going to put 1, 1, 1, 1 to represent that this is the information concerning only the first stage. So what will happen is, here on the reactions, I'm just going to put R just to make things simple. This will be R inlet, and then the relative velocity of the exit velocity of the steam and the velocity of the blade, we are going to say it's R2 exit. It's R exit rather, not R2. R exit number 1, and then this is R inlet number 1, representing that this is the information of the first stage. U will be the same on both the diagrams. That is why you can tell that we transferred the measurements straight from the diagram of the first stage. So now this air will glide through the first one, the first stage, and then be redirected by the fixed blade to enter what? The second stage, which will be represented by this one. The velocity at which the steam will leave the fixed blade will be represented by this. Let's take this as our nozzle. We take the fixed blade as our nozzle, and then what we are going to have is, let's say our nozzle is here, which will be what? The fixed blade. The steam is entering V initial. Now we are dealing with the second stage. We are going to put number 2. And then in this case, you can tell that this is 90 degrees, meaning what? We are dealing with a velocity diagram that discharge axially only on the second stage. The steam is being discharged axially. How do we know? This being our beta number 2, it's 90 degrees. So the reason why this is called beta number 1 and this is beta number 2 is because they are not the same. You might be told that they are the same, but it's not always the case where you are going to have them being identical. So we have to represent it by saying this it's alpha 2, this theta 2, this is phi 2. This is the inlet velocity, that which will be the velocity at which the steam is leaving the fixed plate entering the second row, and then the velocity at which the steam is leaving the second row, it's not final, it's exit. And then relative velocity number 2 initial, then the relative velocity at the exit, it's also number 2. So there is nothing new. What you have to do is to listen to the information that they are presenting to you. Because as we were drawing the velocity diagram in N5, where we only had this diagram without this diagram, you also need to listen to what they are telling you so that you are able to get the information or the values concerning both the diagrams, because they will give you information for this only and give you information for this only. What you know is that this U will be equal to this U. That is the only thing that you know. The diagrams, if they are the same, they will tell you, but you must treat them as being different values. As you can see, this is theta 1, this is theta 2, representing that they are not the same. This is VI2, this is VI1, they are not the same. So we have what we call K. K is the frictional coefficient, or the coefficient of friction, if you may. The coefficient of friction, it's telling us about the friction that the steam experiences between the inlet as it enters the blade, or we can say between the inlet of the blade and the outlet of the blade. So let's take, you are given VI1, and then you are told that the coefficient of friction, it's equals to, let's say 90%, or they can give you as 0.9, which is the same thing we know. So what this tells us is that if we want to get the value of VE1, which is the velocity of the steam as it is leaving what? The blade, we are going to say VE1, it's equals to K times VI1 1, which is inlet. This tells us that as the steam is entering the blade, only 90% of it, or 90% of the velocity, was measured at the outlet of the blade. Due to what? Due to friction. Or we can put it in another way and say 10% of the speed of the steam was reduced as it was gliding through the blades. Why? Because of friction. The same thing will happen. The steam is leaving what? It's entering the nozzle at VI1. It's leaving the nozzle, entering the blade at VI1 rather. And then it's leaving at what? VI2. We are reducing by 10% because of what? Of friction. Now, the steam is leaving the second plate, the first plate, sorry, into the fixed plate. And then as it is coming out of the fixed plate, remember, we also take K into consideration, meaning that our V, the velocity at which the steam will leave the plate, will be V initial number 2, because that will be the velocity at which the steam will enter the second row. Then it will be VI2. So to get our VI2, we are going to say we are only left with 90% from what we had. What is it that we had? What we had, it's VE1, because that is the velocity at which the steam entered the fixed plate, which will be VE1. We do take into consideration what the coefficient of friction. Even if now you are looking for VE2, which is the velocity of steam at which the steam will be leaving what? The second plate. And then it will be, take K into consideration, times what? VI2. Because we are reducing from what? From the recent velocity of the steam. The steam entered and then it was reduced, the velocity was reduced, 10% of it gone, and then it comes out on the other side. Now we take into consideration the value of K. So if you're given the value of K, you must take it into consideration. As it was entering the first row, fixed plate, and the second row, we take it into consideration. Unless you are told that the coefficients are not equal, or you are told that here we are having the coefficient of friction as so and so, and then we are told that here there is no friction, or you are told that here there is no friction. In that case, you are only going to consider the coefficient of friction only where you were told to consider it. So the coefficient of friction, you can also use them to get the relative velocities. So you are going to say the relative velocity that you are given, and then times it by the coefficient of friction which we are given. We are going to get this value. And then you say this value times by the coefficient of friction that you are given, we are going to get this value. Same thing, we are going to get this value. So it works on both the velocities, the velocity of the steam and the relative velocity of the two. But they are the same always, unless you are told you don't know about this. And these are some of the equations or the formulas that we will be using in this section. We are having the formula to calculate power, which is given by mass times the blade velocity plus W1 and W2. W1 and W2 will be this one being our W1, then this one being our W2. So we are going to say W1 plus W2. And then we have the blading efficiency, which is given by 2 times the velocity of the blade times W1 plus W2, all divided by VI1 raised to E, which is the number of stages. And then we have the formula to calculate our axial thrust. It's given by mass in bracket, another bracket, the velocity of flow number 1 minus the exit velocity of flow number 1, that's stage 1. Close the bracket, plus the inlet velocity of flow, that is the number 2, and minus the velocity of flow at the exit number 2. And then close bracket, close the big bracket. So the velocity of flows, we know this is the velocity of flow, and also this is the velocity of flow. This will be the initial, that is number 1, because we're dealing with the first stage, and then this will be the exit, dealing with number 1 still. Velocity of flow here, it will be initial number 2, and then velocity of flow this side, it will be initial, its exit rather, number 2. So that is what it's where we get our velocity of flow. So yeah, that's basically what we need to start attempting questions. I will see you on the next lesson.